We all learn pretty early on how to find the area of simple shapes, right? Like squares, triangles, circles, those neat little formulas where everything just fits together nicely. But have you ever wondered what happens when you come across a shape? A shape that has like a really crazy curvy boundary. All those simple tools, they just kind of fall apart, right? I mean, at least for me, that always kind of left me wondering, is there any way to actually get a precise measurement for these, irregular areas? And, well, that's actually the very puzzle that we're going to be taking the deep dive into today.
Yeah, you hit the nail on the head. Those basic geometric formulas, while fundamental for regular shapes, just don't quite cut it when you're dealing with curves. It's like trying to fit square pegs into round holes. It's actually in this very challenge, I think, that the real ingenuity of integral calculus really starts to shine through.
It does. Yeah. So in this deep dive, we're going to be exploring how integral calculus offers a powerful method for calculating these areas enclosed by curves. And we're going to be building upon an idea that we've touched on before, which is this notion that a definite integral can be seen as the limit of a sum. Think of this as like extending that concept to the realm of shapes with curves, going beyond those neat straight lines. And our guides on this journey, the sources we're dipping into, are excerpts from a mathematics textbook that really delves into the practical application of these integral tools.
And as we set out on this exploration, I think it's really worth keeping in mind a quote from Birkhoff, who said, "One should study mathematics because it is only through mathematics that nature can be conceived in harmonious form." And I feel like this really sets the stage for appreciating the inherent elegance and the underlying order that integral calculus brings to our understanding of area.
It does, doesn't it? It suggests that beneath these seemingly complex curves and shapes that we encounter in the world around us, there's this mathematical harmony just waiting to be discovered.
Okay, so let's start getting a bit practical here. Let's imagine a simple curve defined by y equals x like x, right? Between 2 points on the x-axis. We can call those points 6x and 6x as $. Now, what would be the fundamental approach using integration to finding the area that's trapped beneath that curve?
So the core idea here is to take that area under the curve and mentally slice it, like a loaf of bread, into an enormous number of incredibly thin vertical strips. Picture these strips as so incredibly narrow that they're practically lines themselves. And each of these strips has this tiny width, a little sliver, that we represent as $6. Now, the height of each of these strips is determined by, well, the height of the curve itself at that particular x. And that's represented by the y value, or 8 is that point. Right. So each of these incredibly thin rectangles has a tiny area, which we can call dO. And because its height is width is that tiny little duals, we can say the dale is simply day times dgale, or to put it in terms of our function, it's def d as e times day.
Precisely. Now, to get the total area under the curve from day to dollars, we essentially need to add up the areas of all these infinitesimally small strips. And this infinite summation is exactly what the definite integral represents. So the total area, which we can call unday, is given by the integral of dfc, and we calculate that from a to fx. That's written as imb fx. Just a reminder that elongated s symbol is the integral sign, and it essentially represents that process of continuous summation.
That makes sense intuitively. We're taking this complex problem of finding the area of this irregular shape, and we're breaking it down into the problem of adding up an infinite number of these super simple areas. So, I mean, could we approach this in a different way? Like, what if instead of using these vertical strips, we decided to use horizontal ones? Is there ever a situation where that might actually make more sense?
Absolutely. That's a really insightful question. Sometimes it's actually much easier to use horizontal strips, especially when dealing with a curve that's defined as, let's say, $6 equals dy. Now imagine we're interested in the area that's bounded by this curve, the y-axis, and two horizontal lines, gyu and y equals d dollar. Our source illustrates this nicely in figure 8.2. If we slice this area into those thin horizontal rectangles, each strip will have a height of d dollars and a length that's determined by the x value on the curve, which is 6x equals by. So in this case, our tiny area becomes times d, which is above as dy times dy. And the total area would be the integral of g d pi from 2 day. So int gx int dy a die. The choice between vertical and horizontal strips often boils down to which orientation gives us a simpler function to integrate.
Okay, I can picture those horizontal slices. Now let's get into a tricky situation. What if our curve dips below the x-axis, within the interval we're considering? How does integration handle that? How do we account for that area that falls below the x-axis?
That's a really crucial point to consider. You're right. If our curve, x, decides to venture below the x-axis between x equals b, the function 5x is going to have negative values in that section. And as a consequence, the definite integral dmxc is also going to give us a negative value for that portion. But when we're talking about geometric area, we're generally interested in a positive quantity. So if the curve happens to be entirely below the x-axis, as our source shows in figure 8.3, we take the absolute value of the definite integral to ensure we get a positive area that looks like this. Dmx dxe.
I see. So the integral itself gives us a signed value, telling us whether the area is above or below the x-axis. But the actual area, the physical area, is always considered to be a positive value. Now, what happens if the curve gets even more adventurous and decides to cross the x-axis within our interval between a head and the dollars? Like it goes above and below. How do we deal with that?
In that scenario, we'd have a situation, as depicted in figure 8.4, where the curve contributes a negative area in one part of the interval. Let's say that's $1 because it's below the x-axis, and then a positive area in another part, let's call that $2, where it's above the x-axis. The total geometric area bounded by the curve and the x-axis would be the sum of the absolute values of those two areas. We would write it like this: $8 plus A22. To get there, we need to figure out exactly where the curve crosses the x-axis, meaning where 5x equals 0. Then we'd split our integral into separate integrals over those smaller intervals where the curve is either consistently above or below the axis. And finally, we take the absolute value of any negative results before adding them all up.
Right. So we need to make sure we're treating those areas above and below the axis as positive contributions to the total area.
Okay, so far so good. Now, let's take a look at how we can apply these ideas to some familiar shapes. Our source kicks things off with a real classic: the area of a circle. That simple equation, x by dollars plus y2 equals a22. How can we use the power of integration to arrive at that well-known formula? The circle is a great starting point because it's so beautifully symmetrical. As figure 8.5 shows, we can simplify our task by zeroing in on just the first quadrant, the region that's labeled AOBA. Now, thanks to that symmetry around both the x and y axes, the total area of the circle is going to be exactly 4 times the area of this first quadrant. In the first quadrant, the y values on the circle are all positive, so we can express y as a function of $6, which gives us a scoredy. If we use our vertical strips method, the area of this first quadrant is given by the definite integral Cporty AO2 by 2x day. Then, to find the total area of the entire circle, we simply multiply that result by 4. $4 day 2 by 2 ds step.
Okay, I'm following you. Setting up the integral itself seems straightforward enough. But that square root term, that square dA2 by 2 augment, how do we actually go about evaluating that integral? It doesn't seem like we can just use the power rule here, right?
You're absolutely right. We need something a bit more sophisticated. We're going to employ a technique called trigonometric substitution. That form, square A2 by 2, kind of hints that a substitution involving sign might be the way to go. So if we let x as sin theta, then lambda becomes a cos theta, d theta. Now, as theta ranges from 0 to a, the angle theta ranges from 0 to frac. Let's substitute all this into our integral. We get $4 in cos theta d theta. This simplifies to $4 in cos theta d theta t theta theta 2 theta. This simplifies to $4 in the cos theta t theta cos theta shadow 4a2 by cos theta further. Now we can use a handy trigonometric identity, which is cos theta frac 1, to finally integrate. After all that, the result turns out to be 4a2 left frac theta fried 4a2 left plus 0 right. And there we have it. The familiar formula for the area of a circle elegantly derived through the magic of integration.
That is so cool. Seeing that fundamental formula pop out from these more general principles of calculus is incredibly satisfying. And I love how our source also points out that we could have used horizontal strips instead, integrating with respect to y. Figure 8.6 illustrates this. We'd integrate sec(x), coordinate 2y2 from dollar to y, then multiply by 4, and we get the exact same result, a2 into 2. That consistency really highlights the power of these methods.
Exactly. Whether we choose to use vertical strips or horizontal strips is often a matter of convenience, whichever one leads to a simpler integral. But the underlying principle of summing up those infinitesimal areas remains rock solid, regardless of how we choose to slice it up.
Okay, now let's try our hand at another classic shape, the ellipse. The equation for this one is a little more involved. Fraspar2 plus frashadu. How does integration help us find the area of an ellipse?
Just like the circle, the ellipse is beautifully symmetrical about both the x and y axes. Figure 8.7 demonstrates this. And because of that symmetry, we can focus our attention on the first quadrant, calculate its area, and then simply multiply that result by 4 to get the total area. So in the first quadrant, we can rewrite our equation to get Yakko in terms of sextile. If we decide to use vertical strips, the area of the ellipse is given by $4 dx frac smako dx frac meto 2 by t2. Wait a minute, that looks familiar. Isn't that the same integral we solved earlier when we were working with a quarter of a circle with radius agar? The one that turned out to be frac 2 what? You've got a sharp eye. Recognizing those connections is key in this game. If we substitute that result back into our expression for the area of the ellipse, we get frac p AABU, and that's it. The general formula for the area of an ellipse. And notice, if we set both $8 and dollars to be equal to $2, we get pi r22, which, as we know, is the area of a circle. So in a way, the ellipse formula is like a generalization of the circle formula, right? And as figure 8.8 shows, we would actually get the same result if we chose to use horizontal strips instead. We'd integrate 6x over I2 from dollars to ballers and then multiply that by 4. Same result, just a different approach.
That's so neat. It's like the circle formula is just a special case of the ellipse formula. Okay, so we've explored finding areas under single curves, which is awesome. Now, what if we want to find the area of a region that's bounded by both a curve and a straight line? Like, how do we deal with that combination of boundaries? That seems like a very practical application of these ideas.
Absolutely. And our source provides some really clear examples of just that. Let's imagine we want to find the area that's bounded by the curve, let's say 1 by 2 $2 in a simple horizontal line, 1 by 2 $2. If you take a look at figure 8.9, you can see that the parabola 1 by 2 2 is symmetrical about the y-axis. We're interested in the area that's trapped between this parabola and that line.
Looking at the figure, it seems like they've chosen to use horizontal strips for this calculation. Why is that the best approach here?
Well, when we use horizontal strips, our variable of integration becomes 0 and 4. So for any given y value between 0 and 4, that horizontal strip extends from the left side of the parabola, which is 6 squarties, all the way to the right side, which is 6 mu. So the length of each horizontal strip is going to be squarty, which simplifies to $2, and its height is just a tiny daager. So to get the total area, we integrate this length with respect to y from dalers to 4. Looks like this. Dal of 4. And when we evaluate this integral, we get left frac 43, 0, 4, 4, 3, 0, 4, frac 8, y was 0.
That's really direct. But I see that our source also shows how we can tackle the same problem using vertical strips, which is illustrated in figure 8.10. How would that method work, just for comparison?
Sure. When we go with vertical strips, our integration variable is $6. Now, the height of each of those vertical strips is going to be the difference between the I value of the upper boundary, which is our line y1244, and the I value of the lower boundary, which is our curve, our pi's by 2 2's. So to figure out the limits of integration, we need to find the x-coordinates where the parabola and the line meet, right? So setting $6 equal to 4 gives us 6x circle and units 2 to 2, and 6x equals to $2. So with all that said, the area is given by this integral. When we evaluate this, we get left 4x frac by 3, right is 8 plus frac of 3, 16 frac by 3. And as you can see, we arrive at the same area, which is always a good sign, right? It means we're on the right track. And our source correctly points out that although both vertical and horizontal strips can often be used, sometimes one approach might be a bit simpler than the other, depending on the specific curves involved. And vertical strips, I have to say, are often a pretty solid first choice.
I like that. It's a great reminder that we often have multiple tools at our disposal, and sometimes it's a matter of preference or what looks easier, right? Let's take a look at another example from the source. This one combines a line and a circle. So we're asked to find the area that's in the first quadrant, bounded by the x-axis, the line y equals xc, and the circle $6 plus y2s plus 32, 2. How do we tackle this one?
This example requires us to be a bit more strategic. If we look at figure 8.11, we see that the line 1y poils in the circle $6 plus y2 equals 3d2, 2 meet at the point B, which has coordinates 4. This is in the first quadrant. The x-intercept of the circle in the first quadrant is at sexy equals squart, which is the same as $4 squart. Now, the region we're interested in, we can naturally divide it into two parts. One is the area under line yxe from 6x equals 6 circles to 6 equals 4 is 3. That's a simple triangle. And then we have the area under the circle given by Segorya score by a 2 from 6 dials to 6 secs is 4 seconds and 3 2.
Right. So for that first part, for that triangle bounded by the x-axis, yawing x size and 6 size I width for 2, the base and the height are both 4. So the area, using our basic geometry knowledge, is simply fraf 1 leads right. How does integration verify this?
If we use integration for the triangular part, we get the area under the line yx from $6 to 6 equals 4/4, which is, let's see, 4x dx left right at $16 a to 4. And as you can see, it matches up perfectly with our geometric calculation. Now, to get the area under that circle segment from 6x to 4, 6 for circle total, we need to evaluate this integral. In the square to sort of circle 2, this is going to require another trigonometric substitution, letting 6x 4 circle total. After doing all that integration magic, the result is 4 we're sorting it up. Now, to get the total area, we add up the area of the triangle, which is 8, and the area under the circle segment, which is 4 androns. That gives us a total area of $4.
I love that strategy of breaking down a more complex region into simpler shapes that we can handle with integration. It makes the problem so much more manageable. Now, the source throws in another interesting case that involves an ellipse and a couple of vertical lines. It asks us to find the area bounded by the ellipse frac height 2 plus frac height 2, and the line 6 equals an e 6x to the 2, and it also mentions this relationship where $2 is a to 1, 2 to the d equals 1, where e is the eccentricity and it's less than 1.
Right. If you look at figure 8.12, it shows the region we're dealing with. The nice thing is it's symmetrical about the x-axis. So we can calculate the area in the first quadrant that's bounded by the ellipse in the x-axis, and then simply multiply by 2. In the first quadrant is going to be equal to frac down to 2. So the integral we need to solve is this. $2 in t discato, e to a's greatest a, e dx dat a, dx abs t e 2 by d. Again, a trigonometric substitution will be helpful here. Let's try sextosis and theta. And after we do the integration, the area turns out to be this. ATE e to gauto. This result elegantly connects the area of this specific part of the ellipse with its eccentricity, which is a measure of how stretched out the ellipse is.
It's fascinating how a geometric property like eccentricity has this direct impact on the area we calculate through integration. It shows how interconnected these concepts really are. Okay, let's shift gears a bit. We've been focusing on finding areas under single curves. But what about finding the area between two different curves? Now, that seems like a really practical application of integration, right? Like something you'd see in the real world.
Absolutely. This is where it gets really interesting. So let's imagine we have two curves. We can define them as frx and fsrx and f right equals self g exit. And let's say they're defined over an interval. We can call it AAAB. Now, if AXX is greater than or equal to, for all 6 values within that interval, meaning the graph of phi rex was always sitting above or just touching the graph of x, then the area between those two curves is the integral, the difference between those two functions. And we can write that as a dx dxa.
That makes sense intuitively, right? We're basically calculating the area under the upper curve, which is I-thing axis, and then subtracting the area under the lower curve over that same interval. And what's left is the area tracked between them.
Exactly. Our source makes a great point that this is equivalent to taking the definite integral of 5 from 8f(d) to $, and then subtracting the definite integral of dx from 8x to x at gxe. But there's a bit of a wrinkle. What happens when those two curves decide to intersect within the interval 8b day? As figure A$14 shows, in those cases, xx might be greater than some parts and the x might be greater than 5x in other parts.
Right. So if we just blindly applied that formula, dx, gx, dxc, we might end up with a net area, a signed area, that doesn't actually reflect the total area enclosed by those curves.
Exactly. So to get around that, the first step is to figure out the x-coordinates of all those intersection points within our interval, leave b. Let's say, for simplicity, that they intersect at a single point, 6 equals NLCASE, and this point is somewhere between a c and a $. So we need to break down our integral into separate integrals over those smaller intervals where one function is always greater than the other. The total area is then the sum of those integrals, but we use the absolute value of the difference between the functions to make sure we're always adding positive area contributions. So if face dollar is greater than or equal to DSCB, ACX is greater than or equal to FC in the interval TA, then our total area would be EC ACX dx plus EFD GX dx dx.
That makes sense. We have to be a bit careful to make sure we're always adding positive areas. So let's take a look at a specific example, example 6. In this one, we're asked to find the area that's bounded by the parabolas is by $2 and $20 by $11, $2. How do we start this one?
The first step is to figure out where these two curves intersect. If we substitute Giles by 2 3a's into the second equation, we get pi 2 curves of x by $2 as before is say. This simplifies to 6 by $, is a less, or x explains $, equals level. Factoring that gives us 6 by $3 behind. So our solutions are 6 of dollars and 6 of wheels even, and the corresponding y values are y and a border 1, as shown in figure 8.15. Now we need to figure out which curve is above the other one in the interval from 0 to 1. To do this, we can just pick a test value, like 6x or a 555. When we plug that into the first curve, y.52 equals I.252 tos. And on the second curve, y.4 which is about some 0.5, which is about 0.707. So in this interval, the curve is above the curve y5 2 tax. So the area between them is given by y by 2.
And if we evaluate that integral, we get
T called by 212, left 3 by 3 by 3, and a 3, y by 3 by 3 is 0.0000055. So the area trapped between those two parabolas is exactly fracs with 2.
nice. That's a pretty clean result for a problem that seemed potentially messy. Now, how about example 7? This one asks for the area that's above the x-axis, and between the circle 6 pi dollars plus y2 equals 8 pi dollar, and inside the parabola, twi dollar equals 4 pi dollars. This one seems like a fun challenge.
It does. It brings together a lot of the techniques we've been talking about. So first, let's rewrite that circle equation. We can put it in a more standard form like this. 6 by 4, 2 plus y2 equals 16. See so what? Now we can see right away that the circle has its center at 4, a 0, and a radius of 4. The parabola, on the other hand, with the equation $20 4 by over, has its vertex at the origin and it opens to the right. Now to find where those two curves intersect, we can substitute twi dollars 4 by dollars into our circle equation. So we get 6 pi dollars plus 4x equals 8 pi dollar, which simplifies to 6 by 4x equals 1. Factoring that gives us 6 by 4 equals $1. So they intersect at 6 pi dollars and 6 equals 4.3. The corresponding y values are 0 and plus or minus 4. Now remember, we're only interested in the area that's above the x-axis. So the intersection points we'll use are 0, 0, and 4, 4. Take a look at figure 8.6.
Okay, I see it. So the area we want is bounded by the parabola from $6 to 6 equals 4.3, and then by the top half of the circle from 6 equals 4 to 6 equals 88, which is where the circle crosses the x-axis.
That's exactly right. So we break this area down into two parts. Part 1 is the area underneath the parabola, scored more $6 to 6 dollars 4.2. And part 2 is the area under upper half of the circle, scored at 8 by 4 from 6.4 to 6 otters is 80L. So our total area is the sum of these two integrals. Lenny 4 to 6, Lenny Vix plus 6 quarter 5 by 4 plus Lenny Vix. Okay, and what do those integrations give us?
Okay, so that first integral, Lenigolese, turns out to be left Zorn 5.3 blind right. Now for that second integral, Nendial 3 Gini always, we can make a substitution. Let's try $1 is 4.3. This transforms the integral to Linivor Sor Do. And this is something familiar. It's just the area of a quarter of a circle with a radius of 4, which we know is frac or 2. So when we add up both parts, we get frac 3 plus 4 pi for the total area. I'm really starting to see how all these techniques fit together. It's like we can take these fundamental ideas and apply them to all sorts of different scenarios. And I noticed that our source even throws in examples of finding the area between an ellipse and a chord, calculating the area of a triangle using integration, and even finding the area enclosed by two overlapping circles.
It's amazing, isn't it? Each of these examples just showcases the versatility of integral calculus. Example 8, with the ellipse and its chord, involves first finding the equation of the line for the chord, and then integrating the difference between that line and the ellipse. Example 9, where we use integration for a triangle, even though it's kind of overkill, really illustrates the power of the method. We're essentially summing or subtracting areas under lines to find the area of a shape we already know how to calculate with simple geometry. And then example 10, with those two overlapping circles, is super clever. It uses symmetry and requires us to integrate segments of both circles.
It all comes back to that fundamental idea, right? The idea of summing up those tiny areas to get the total area of a shape, no matter how irregular or complex it might be.
Exactly. And it's important to remember that these techniques we've been exploring have deep roots in the history of mathematics. This idea of approximating areas by using simpler shapes goes all the way back to ancient Greece, and a method called the method of exhaustion. Mathematicians like Eudoxus and Archimedes used this method to figure out the area of a circle. It was a critical precursor to the development of calculus as we know it today.
Wow, that's incredible. To think that those early geometric explorations paved the way for the powerful tools we use now. And then, of course, in the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz, they both, independently of each other, really formalized these ideas into what we know as calculus. It's kind of mind-blowing when you think about it.
It is. Newton called his approach the theory of fluxions, and he was really focused on rates of change. Leibniz, on the other hand, developed what he called the calculus summatorius, or integral calculus. His focus was on adding up or summing those infinitesimally small
And
quantities.
it's fascinating that although they approached it in different ways, they both arrived at essentially equivalent mathematical frameworks, right?
Absolutely. And Leibniz's notation, especially the integral symbol, that elongated S, directly represents that concept of summation, of adding up those infinitesimal areas. And he was one of the first to really recognize